Hello guys, welcome to Ramta Solutions and welcome to your last video on grade 10 electric circuits. In this video, what we are doing is simply to summarize what you have done so far or what we have covered so far in the topic, and of course covering other aspects that we might not have covered in the previous videos. For example, we're going to look at how we connect the ammeter and maybe give more insight on the ammeter, and of course talk about brightness. And we will also be talking about some things when it comes to a relationship between potential difference current and resistance. Okay, so the order of, or rather the scope of this video, what we're going to do in our summary, we're going to talk about the definitions and formulas that we learned so far, resistor connections, which was your series and parallel combination, and also what we said about the relationships between potential difference, current, and resistance. Then conclude the lessons by touching a bit on connecting the ammeters and the brightness. Okay, so this is the video that I think will sort you out for the entire FET phase, your grade 10, 11, and 12. Because if you know all these things that are being covered in grade 10, trust me, grade 11 and 12 electric circuits will be easy for you. Okay, so without any waste of time, let's get into it. Now, oh boy, let me use a red color, a black color in fact. So we talking revision and summary. So we're talking revision and summary. So we are going to begin this with 1.1. What is it? It was definitions and formulas, of course. Definitions and formulas. Definitions and formulas. So the key formulas that you learned so far was 1. Potential difference is W over Q. Current is Q over delta T, and one that you've been using your whole life when you came across electric circuits, R equals V over I. So this is potential difference. I'm going to write it as using a small font size. So this is potential difference. The definition of potential difference was, so let's see, we said potential difference is the work done per unit charge, right? Is the work done per unit charge? Is the work done per unit charge? All right. Now moving on to current. Let me underline this. Now moving on to current. What is current? So current is the amount of charge passing through a point in 1 second. Is the amount of charge passing, I think I should say passing through a fixed point, right? So passing through a fixed point in 1 second. Okay, in 1 second. That is the definition of current. All right. Now, when we talk resistance, what we said about resistance was it is a measure. Let me do this. Resistance. We said resistance is the measure of how hard it is to push electricity through a circuit element. But I'm going to give you more definitions on this. Okay. Resistance is the measure of how hard it is to push electricity through a circuit element. through a circuit element. Okay. Now, another definition that you can use is this. You can basically say resistance, instead of saying it is the measure of how hard it is to, instead of saying it is a measure of how hard it is to push electricity through a circuit element, you can say it is the opposition to the flow of charge, right? You can say it is the opposition to the flow of charge. Or, because you have a formula, you can say resistance is the ratio of the potential difference to the current in a circuit. That's it. A ratio of the potential difference. Maybe add more information to this thing. Say it is the ratio of the potential difference across a resistor to the current in the resistor. But simply a ratio of the potential difference to the current in the circuit. You can call that your resistance. Otherwise, as for me, I prefer this one. It is the measure of how hard it is to push electricity through a circuit element. That is to say to you, you know now that another definition we said was it is opposition to the flow of charge. The higher the resistance, the lower the current. Alright? The higher the resistance, the lower the current. Alright? So if you have high resistance, you will have low current. If you have low resistance, you will have high current. Okay, remember, resistance is the measure of opposition to the flow of charge, or measure of how hard it is to push electricity through a circuit element. Okay. All right. Now, resistor connections. That's the next point. Resistor connections. Oh boy. Use black color. Resistor connections. Resistor connections. So with this one, what we are saying, we know that our resistors can be connected in series. So I'm going to divide the page by saying, one, we will look at series connection, and we will also look at parallel connection. Okay, don't know why I'm struggling to write this. Series connection, and then parallel connection. I'm going to divide this. I have lines. Let me use my lines. Yeah, you see, much better. Here, this must move a bit. Oh, it's ugly, eh? But it's all right. So, a series circuit, for example, we have something like this. Let's say this is your ammeter. Let's say this is your right? So this is your R1, this is your R2, this is your R3. Now, with this one, we will say this is your ammeter. Let's say this is your R1, 2, R3. Okay. Boop. Okay. So, now let's sort it out. This is your R1, this is your R2, and this is your R3. Okay. What we said with this one, we said here, current is the same. All right. Here we said current is the same, meaning the total current, whichever current that is flowing wherever, the total current will be equal to the current flowing at resistor 1. It is the same as current flowing at resistor 2. It is the same as current flowing at resistor 3, and so on, when they are connected in series. Now, when they are connected in parallel, we said current is divided. Remember, when we say divided, we say it's split. For example, I said to you, when you draw electric circuits, draw an outward arrow to say this is the direction of current. As you can see, current is not split because no joints here. All right, but here, as you can see, current will be split when it gets to this point. One will be going that way, one this way, and the other that. So here, the total current will be equal to current flowing at resistor 1 plus current flowing at resistor 2 plus current flowing at resistor 3, and so on. Okay. Now here we said potential difference is divided. Okay. Potential difference here is divided. Potential difference is divided. Okay. What about here? Potential difference is the same for resistors in parallel. Okay. Potential difference is, this was a very big writing. Potential difference is divided. Oh, sorry, is the same. Is the same. Right, for parallel combination is the same. Okay, so what does it mean? What it means here is that since we say it's divided, this means total potential difference is equal to potential difference of resistor 1 plus potential difference of resistor 2 plus potential difference of resistor 3, and so on. Now with this one here, for parallel combination, we said potential difference is the same. What does it mean? It means potential difference, total potential difference. Of course, when your circuit, when all resistors in your circuit are connected in parallel, it will be total potential difference or potential difference for a parallel connection. Maybe let me call it this. Potential difference for a parallel connection will be equal to potential difference of resistor 1 will also be equal to potential difference of resistor 3 will also be equal to potential difference of resistor 3, and so on. So that is to say, these resistors that are connected in parallel, they have the same potential difference. Okay, they have the same potential difference, which we can call VP, meaning potential difference for parallel connection. Or if you like, if your circuit only has resistors connected in parallel, it is that potential difference supplied by the battery. Okay, perfect. Now, concluding, let me return my line. Okay, returning my line. Total resistance. Okay, total resistance when resistors are connected in series. Allow me to call it R sub S for series, will be resistance of resistor 1 plus resistance of resistor 2 plus resistance of resistor 3, and so on. Now for parallel connection, total resistance would be 1 over Rp is equal to 1 over resistance of resistor 1 plus 1 over resistance of resistor 2 plus 1 over resistance of resistor 3, and so on. Note, to get Rp, invert the answers you get. Alright? To invert your answers you get. If 1 over R1 plus 1 over R2 plus 1 over R3 gives you, let's say, 2 over 12. Alright? For example, this one I have to edit. For example, 1 over Rp is equal to 2 over 5. This means Rp will be, you need to invert it. Alright? It will be, R sub P will be, one shouldn't say Rp. It means something different. So it's R sub P, because this P is power, which we'll learn next year, right? So R sub P will basically be, like I said, invert. It will be 5 over 2. Remember, invert means what as numerator becomes denominator, what as denominator becomes numerator, as you can see. 2 was a numerator, it will now become a denominator. 5 was a denominator, it will now become a numerator. Therefore, what does it mean? R sub P is equal to 2.5 ohms. Okay, so this is how you do it. Okay. Now, we then are going to look at a relationship between voltage or potential difference, current, and resistance. That's 1.3. A relationship between, oh boy, let me write let the words in full, between potential difference and resistance. Okay, we know R equals V over I. Now, for total circuit, okay, for total circuit, this is one thing I want you to know. V is constant. What I mean is that potential difference applied by the battery is constant. That one is a fact, it doesn't change. For total circuit, V is constant. Okay, therefore, what does this mean? When V is constant, we can therefore say R is indirectly proportional to I. What is the implication here? The implication here is that when R increases, current decreases. And when R decreases, current increases. Okay, this is what you need to know when we're looking at the total circuit. Okay, when we're looking at the total circuit, this is what you need to know. When total resistance increases, total current decreases. When total resistance decreases, total current increases. This is for total circuit. Okay. Now, let's look at for individual circuit components. For individual circuit components, I don't know why I had to write individual circuit, but it's fine. For individual circuit components, meaning your bulbs and whatever that you're connecting into your circuit, your resistance of those components, in other words, maybe your bulbs, your whatever that has a resistance, resistance will be constant. Okay, resistance will be constant. Okay, resistance will be constant. Okay, resistance of your individual components in your circuit, your resistance is basically the same. Now, what happens if this is the case? Remember, we're saying R is equal to V over I, and we're saying what is this? We're saying resistance is constant. So this then becomes, look at it, I is equal to V over R, but this guy is constant. Therefore, we can say, I is directly proportional to V. All right, I is directly proportional to V. So what is happening? This therefore implies if current increases, potential difference increases, because this is directly proportional. And if current decreases, potential difference decreases. Okay, remember guys, this is for individual circuit components. Okay, this is for individual circuit components. You will see this example, or you will see the application when you do your past papers, and I will remind you when you do them. Okay, now I also need to say something. Now let's look at for parallel connection. Okay, for parallel connection, or maybe let's do this. Because I'm relating this, let me again return my line, because I need to really ensure that you guys have all things that you need and ace this topic. Okay, in fact, this time around must be straight, otherwise. All right, perfect. So now let's look at the series combination and series connection and the parallel connection. So for series, if R is removed, all right, if R is removed, what happens? If R is removed, what happens? Total resistance increases. total resistance, decreases. What happens when total resistance decreases? This means total current will increase, right? Remember, in series, we now looking at for total connection, right? If R is removed, total resistance will increase, right? So this is for total. Now, if this is the case, what does it mean for individual? What does it mean for individual components? So for components, right? For components, what does it mean? It means potential difference will decrease. Okay. Now, what if R is added? When R is added, meaning resistance, total resistance is increased. What happens when total resistance is increased? This means total resistance of the circuit increases. What does this mean? This means total current will decrease. Remember, these guys have an indirect relationship. Okay? They have an indirect relationship. Now, what does this mean for components? For components, you must highlight the point here. Remember, voltage for components is directly proportional to current. This means voltage of the components will decrease. I repeat, voltage of the components is directly proportional to the current. Okay? Remember, voltage of your total circuit is constant, but of your individual components, it depends, or it is related to current, because the resistance of components are constant. All right? Now, let's look at parallel connection. If R is removed, okay, if R is removed, this means RP, okay, if one of the resistors in parallel is removed, this means RP, what happens with it? RP increases. And this implies RT increases. Okay. This implies that RT increases. Now, if RT increases, this also implies that current decreases. Right? This means that current decreases. Here I'm talking total current. Total current decreases. Now for components, right? For components, what will happen? Remember I said for components, voltage will be related to the current. The total current flowing will decrease. So since the total current flowing will decrease, what this means is that the voltage or the potential difference of the components will decrease. Okay. So this is if one of them is removed, or again, if maybe it's two resistors in parallel. If one of them is removed, you basically are left with a series combination. But if it's three, what will happen when you remove one? The total resistance, or the parallel combination, total resistance of the parallel combination increases, thereby increasing total resistance of the circuit. Now, if R is added, let me say R is added. What will happen when you say R is added? That means you are increasing more resistors in parallel. What will happen? What will happen when you add more resistors in parallel? When you add more resistors in parallel, what will happen? RP will decrease. It's a fact. RP will decrease, right? And when RP decreases, this means total resistance also decreases. And this also implies total current. What happens? Remember, for total resistance, total current is indirectly proportional to resistance. So total current will increase. Now, for components in your circuit, what will happen? Oh, potential difference of the components will increase because their current has increased. Remember what I said? With the components, potential difference is directly proportional to the current flowing. Okay, but with the total circuit, resistance is indirectly proportional to current, because with the total circuit, potential difference is the same. Okay, so this you will see when we do questions and past papers. Okay, all right. So what is the next item? The next item is connecting the ammeter. This is point 2, I believe, connecting the ammeter. So when we connect the ammeter, so ammeter should be connected, okay, the ammeter should be connected in series with resistors. Should be connected in series with resistors. Should be connected in series with resistors. With resistors. I'm going to give you some diagrams here to show you what I mean. For example, this is what I mean. Let's try. Okay. So you see, this is the circuit, and this is, I'm just going to take 2 resistors. Okay. And then I'm also going to take this one here. Maybe let's call it, I need to make it a bit bigger. Let me make it a bit bigger. That's not what I meant when I said bigger. I had to take it to the far right, open it a bit wide, and then boom. So let's call this one ammeter A1, and then let's have our resistor here, and let's have our resistor here, and these resistors are at okay. Then and let's call this one ammeter A2, and then yeah. So as you can see, this current is flowing from this direction. Now you see this current, let's call this one resistor R1 and resistor R2, again R1 and R2. So as you can see, this ammeter is connected in series with these resistors. Again, when you look at these ones here, this ammeter is connected in series with resistor R1, and this ammeter is connected in series with resistor R2. Okay, so this is how you connect your ammeters. They should be connected in series with the resistors. Okay. So now, what happens if they are not connected in series? If they are not connected in series. So I need to emphasize something here. If there's one thing that we need to avoid is ambiguity in how we say things. When I said they should be connected in series, I didn't mean that ammeters should also be seen in circuits that have resistors in series only. I didn't mean that. As you can see with this one, it's a parallel combination, but if you look at the ammeter and the resistor, they are in series. Okay, they are not in parallel. Okay, so now the question is this: what happens if they are not connected in series? I'm going to give you an example. So this is what you have. This is your ammeter, and let's say this is your resistor. Let's say this is a resistor R1, resistor R2, and whatever resistance. So what will happen here? A simple thing is this. Your current, it's not flowing this way. Your current is flowing in this way. Your current will be flowing in this way. But because this is the direction of, this is where the ammeter is connected, current cannot go this way. Right? It cannot go this way. It can only move this way. Therefore, what does it mean? There will be no flow. R1 and R2 will not have any charge flowing. Right? So what will happen? This means circuit will be short-circuited. Let me write it in red. circuit will be short-circuited. Alright, circuit will be short-circuited, meaning no current will be flowing. No current will be flowing through the resistors. Will be flowing through the resistors. Okay, through the resistors. Which resistors am I referring to? These resistors. But if we were to add a resistor here, there will be a current flowing here, but not here. So this part will be short-circuited. There won't be any current flowing through it. Okay, or there won't be any current flowing through them. But if we were to add a resistor here, there will be some current flowing here. But here, there's totally no current. Remember, there's totally no current flowing. Remember, an ammeter should be connected in series with the resistors. This ammeter is connected in series with this resistor. It is not connected in series with these ones. Hence, there is no current flowing through these ones. Okay, perfect. Now, I believe we must go to the third point, which is brightness. Now, with brightness, it'll make more sense when you get to grade 11, because you will be doing, what is this? You will be doing power calculations. So with brightness, because you are in grade 10, I'm going to explain it using a grade 10 knowledge. Okay? For grade 10 knowledge, let's say bulbs with equal resistance. Okay, I'm going to say to you, bulbs with equal resistance will have equal brightness. With equal resistance will have same brightness. Okay, can I squeeze this? Let me see. Yeah, will have the same brightness. Okay, now bulbs in parallel are brighter than those in series. Are brighter than those in series. This is because, by the way, this sign means because. This is because parallel gets greater potential difference. Okay. This is because parallel gets greater potential difference. Maybe let me write that. This is because parallel gets greater potential difference. So what I mean here, guys, what I mean here is this. If you are using you are comparing two bulbs, you decide to connect them in series and you decide to connect them in parallel. Brightness of those two bulbs will be greater when in parallel than when in series. Okay. So this is what I'm going to leave you with for grade 10. Bulbs with equal resistance will have the same brightness. And again, bulbs in parallel are brighter than those in series. Why? This is because those in parallel, they get greater potential difference. Okay, they get greater potential difference. All right. So, yeah, this is all that we need. And this is our summary. All that we have done today, guys, is to help you with one, those application questions in your electric circuits, and it is also to help you with your multiple choice questions. Okay, it is also to help you with your multiple choice questions. Okay, so with this being said, ours ends here, and see you next time, of course, with past papers. So, bye-bye.